Hello and welcome to another LeetCode question. Today we're going to be doing the problem from yesterday's LeetCode contest, the hard problem from there. And it's actually, funnily enough, I didn't mean to do this, but it's actually just a little bit more complicated version of the Asteroid Collision Problem that I did yesterday. So if you haven't seen that one, I'd encourage you to watch that one. And if you can watch that one and understand it, and it's pretty straightforward, then this is pretty much the same thing, to be honest. So I'll just read the problem. You're given a bunch of robots, and they are one indexed robots having a position on a line, health, and movement direction. And then you're given a bunch of arrays, positions, health, and directions. All positions are unique. All the robots are moving at the same speed, and if they ever share the same position, they will collide. If the two robots collide, the robot with lower health is removed, and the health of the other robot decreases by 1. And the surviving robot keeps going the same way it was going. If the robots have the same health, they're both removed. And then we have to get the health of the robots that survive the collisions in the same order that the robots were given. So the final health of robot 1, the final health of robot 2, and so on. And so you're given this order, and it's actually in the order, you can think of it in the order of healths or positions or whatever. And return an array consisting of the health of the remaining robots in the same order they were given, after no further collisions can occur. The positions may be unsorted. And yeah, I definitely think this is one of the easier LeetCode contest problems, and if you have seen the asteroid problem, you should be able to do this one reasonably easily. There's just a little bit more prep work for the data because there's more arrays. But let's figure out how this would work. So let's actually go through this example. So in this first example, we're given these positions, and the healths of the robots are these, and they're all going in the same direction. So if they're all going in the same direction, it's pretty straightforward. It means they will never collide, so nothing will collide, and we just return the healths in the same way they're given. Okay. Now let's look at the second example. So we have 4 robots. I'm just going to draw a number line here. So we have 1 at position 2, position 3, position 5, position 6. And so this one's going right with health 15. Right with health 10. Left with health 10. Left with health 15. So what's going to happen is these two robots with health 10 are going to collide, and they're going to destroy each other because they're the same health. And then these two robots with health 15 are going to collide and destroy each other. So then we should return the empty array there. Actually, so one thing here. So this should actually be not 15, this should be 12. So these two robots will collide, and then this robot with health 15 will survive, and it will have 14 health. And that's the answer. Okay. So in the third example, let's draw the number line again. So we have 1, 2, 5, 6 here. Okay. And so we have a robot going right with 10, robot going left with 10. We have a robot going right with 11, robot going left with 11. So this is pretty straightforward. Now they will actually all collide, right? So these two will collide, then these two will collide. And it's pretty straightforward. Okay, so let's try to build some intuition from this problem. And this is going to be, like I said, it's going to be similar to the asteroid problem, where we'll just take, what example do we want to take? Maybe let's just take this example. Yeah. Okay, so what we actually can do here is the positions are actually irrelevant because it doesn't really matter the order that the collisions are in, like which one's closer, and because there's only one way you can have a collision. So there's the only, and I'll actually show this from doing this. The way we actually want to do is we want to process the robots left to right in a stack. And we want to just keep checking the last 2 robots. So let's just show you what this would look like. Like I said, this is similar to the last problem I did. So let's take this middle example here. So we have a robot at 2 that's moving right with health 15. Okay. So we can never have a collision with one robot, so we need to keep adding more robots. And the way we're going to represent these is we're not actually going to care about the position. We just need the position to give us the order of the robot. So we need to process this data and sort it in order of positions. And then we also need to keep track of like the index, but I'll go over that. So we're going to process this data in order of positions, and we're going to put it in a stack. So for this example too, we put this robot down at index 2, with health 15. Now we put this next robot down. Okay. Now it's going right. So now you got to realize the only way, and we're going to keep checking the two robots at the end of the stack for a collision, because the only way there's a collision is if it's the last two robots on the stack, and we're going to have the stack so every single robot is either going the same way or they're going different ways, but there's no collision. So let's go over how you can have a collision. Okay. So if you have a robot going left and a robot going right, you're never going to have a collision with that, right? So this is left, right. This can never make a collision because they're going the other way. If they're going in the same direction, you can also never have a collision, right? So if you're going this way or this way. Okay. And so the only way to have a collision is if they are going opposite directions, and the robot on the left has to be going right. So it has to be like this. And so this has to be right, this has to be left. This is the only way to have a collision. So we can simply check at the end of the stack, and we can just say, okay, are our last two robots going in the same direction or in the opposite direction? If yes, they will collide, and let's just let them collide, figure out the result, and then keep checking the last two until there are no more collisions. So let's see what that's going to look like for this example. So these two are both going right, so they're never going to collide. Now let's add another robot, and like I said, we don't actually care about these indices. I'm just drawing them for the sake of like direction. But all we need for these indices is just to get the order of the robots. We're not actually going to use them in any calculation. And that's one important thing to recognize. So I think in the asteroid problem, these positions weren't given, but you have to realize that the positions don't actually matter. It's just the order that matters. Okay, so the third robot we're going to add to the stack, and it's going this way. And now here, this is going right, this is going left. So these will collide, right? This is the example of the collision. So these will collide. And so what we're simply going to say is, okay, if one's going right and one's going left, then let's have them collide, and let's check the health and figure out what we need to put back. So if one of them has more health and one of them is going to survive, we're going to put that back on the stack. But if they're the same health, we're going to remove them both from the stack. So in this case, we're removing them both from the stack. And now we have only one robot, so we can't have any collisions. Now let's add the last robot. Okay. And so here, this one's going left. It's going left, and it has health 12. And so we need to check the last two robots on the stack, which are actually these two here. And now we do have a right and a left. And so we look at the health to determine which one to put back on the stack. So this one has more health on the left or on the right. So we're gonna pop both to compare, and then we're just gonna push the one with more health and change the health. And so this is going to be removed, this is going to be popped back, and the health will change to 14. Okay? And so now the last robot we have is this. So it's actually a really straightforward algorithm. All we're going to be doing is we're going to be adding robots to the stack and keep checking robots at the end of the stack. And then you might have some scenario where, let's say, you need to keep checking robots at the end of the stack until the length of the stack is either less than 2 or until the last two robots won't collide. Because you can't have some scenario like this, right, where you have 3 robots going right with health, let's say 2, and then one robot going left with health like 14, right? And so you will have a collision here, this will be removed, this will go to 13, and then there will be more collisions. These two will collide, this will be removed, this will go to 12, and then these two will collide. So just because the last two collided doesn't mean you can stop. You have to keep checking the last two elements. Okay, now there are a couple more things we need to do to make sure we actually get a valid output. So we need to return the output in the same order that we had the input in. So that's one thing we need to do, right? We can't just like sort the positions. So how are we actually going to do this? And so I kind of did so if you look at the data, by the way, for all of these are 10 to the 5th. So an n or an n log n solution will work. And obviously we're going to need an n log n solution because we're going to need to sort by positions. So then we can use our stack. And then these numbers are really big, so you don't want to use these. If you have anything that has all of these numbers in a solution, that's not going to work. It's 10 to the 9th. So what we're actually going to do is we're going to actually combine all these values. So we're just going to make an array of like something like this. It'll be position, health, direction, and then the original index of the item. So we can have something like this, and this is going to be, we're going to have this for every single robot, right? So it'll be an array of these. And then that's only going to cost us, 4 times n, which is totally fine, because n is only 10 to the 5th, and we're going to have that. Like there's not really a way around it. We might be able to get a way around it somehow if we just store an array of indices, but an array of indices should technically be O of n as well, so this rounds down to the same thing. Okay, and so we're going to store this. We're going to sort by position. That way we're going to be able to add the robots to the stack by position. And then what we're going to do is, because our outputs on the stack are going to be in this way, we can just use these indices to figure out. So actually, we don't even need to do that. We can just sort by the index at the end. So like, let's say we have a stack with some of these, right? So like PhD1, like a bunch of these, right? So a bunch of these. We're going to have a final stack of robots that we want. We can just sort by this I at the very end. Which is the same time complexity, because that's going to be n log n as well, right? So we're going to have like n log n sort once and then n log n sort at the end. There's other ways you could probably do it if you wanted to. You can make it a result, and then you could actually go by these. But because this is the same time complexity, we're just going to sort twice. And we can totally do that. So that's what we're going to do. We're going to sort, we're going to add all these things together into one array, because we do want to make sure they have, like, we want the same data for the same index to be stored. So we want the robot at position 5 with health 2 and direction R to all be in one, like these things need to maintain the same index. So we're going to store that. We're going to store it like this. We're going to sort it in terms of position. We're going to use the stack, and then we're going to sort in terms of I at the end, and then we can just, for every single one of these, we can print to the result, and then they're going to be sorted in terms of the original order we got. And so this is a really common trick. I think I said this in my other videos. If you want to sort, but you need to maintain the original order, the way you do this, and this happens in a lot of these LeetCode contest problems, the harder ones, is you just add the original index of your item into whatever you're sorting, and then that way, once you sort it, even though they're jumbled up, you still know like where they were to begin with. So then you could if you had a result, let's say the result did have every single item in n items, like there would be no collisions. It would be, you would just have a result. In that case, you wouldn't even need to sort it at the end, because you would have n items, and then you could just go through this list and make a result with a bunch of indices, and then these indices would correspond in where in the result you would print. But because here we're going to have a bunch of robots that collide, we don't really want to do that, because we're going to have a bunch of empty indices. So we'd rather just sort by these indices and then write out into the result. So let's start coding it up. Okay, so we're going to have a robots array. And we can actually, no, this is fine. So I'm going to do like the lazy way of making this array. You could do like an enumerate or a some kind of list traversal thing, but it's not a big deal. So, okay, so we are going to go through every single robot, and we're going to add all these. So remember what we want. So we're going to want the position first, because we're going to be sorting that. We're not actually going to use, like I said, we're not actually going to use the position to do anything other than sort by it. So we're not going to use it in the future, but that's fine. And like I said, this isn't going to add to our complexity, so it's not a big deal. So, okay, so we have the position, health, direction, and now we actually want the index, because we're going to use that to write to the result. Now we're going to sort this. Sort. Jeez. Okay. So now we're going to make a stack, and this is pretty much going to be the same as the asteroid problem yesterday, like I said. So for robot and robots, we are going to append the robot. So append robot. So then we're going to check to make sure the length of the stack is at least 2, because you need 2 elements to have a collision. So while this is the case, we need to actually take the second to last element and the last element, and we need to make sure that they can collide. And so the way that would look like is if there are a bunch of elements in the stack, so like 1, 2, 3, 4, 5. Remember that this element has to be facing right, and this element has to be facing left for a collision. Anything else, there wouldn't be a collision. So we can just check to say if there's anything else, then we can just break this loop. And so we're going to get the second to last element, which is stack minus 2. And then we want the direction, which is at index 2 does not equal right, or stack last element index 2 does not equal left. They both have to be this for it to collide. So we can break here because that means there's no collision. Otherwise, we need to actually pop the two elements. And so that's pretty straightforward. So it's actually going to be last first. And by first, I mean the element on the left. So stack.pop, you need to pop both of them. Stack.pop, and then if first. And so what are we checking? We're actually checking for the health here, which is at index 1. So if the health of the element on the left is greater, then what do we need to do? Well, we need to subtract, right? So we need to subtract 1 here, and then we also need to put it back on the stack. Otherwise, if the health of the second element is greater, or the last, like the element on the right, is greater than first, then same thing, last 1 equals 1. We subtract 1 from the health, and then we append it. Okay, and so what's the last case? So the last case is the health is equal, and if the health is equal, then they're both destroyed, so we don't need to actually do anything here. Okay, so now that we have this, so our stack should contain our outputs, and it's going to be a bunch of these arrays. So it's going to be position, health, directions, I. So now we need to do one last thing, and then we actually need to get the output, but we need to, so we're going to do a list comprehension here. We need to get the output in order of these indices. So we can actually do something like this. So it's actually going to be num1 for num, and then we need to actually sort. We need to sort our stack. So we're going to sort the stack, and then we're going to want to sort it by this right here. And so this is actually, the stack is going to be an array of these items, and then this I is at index 3. So what you can do is if you want to sort by the item at index 3, then you can do something like this. So it's going to be a lambda expression, x, x3. Okay. And then we just want num1 because all we care about is the final health. So this will have a position and health direction. And notice how we never actually use a position in here. We just sort it by position. So that's fine. Okay. And then we just return here. And that should be it, I think. Let's see. Dot syntax. Yeah. Okay, so it's a reasonably efficient solution. Once again, it's not super easy to say. I can definitely make it cleaner, but I just wanted to show the main concepts. And so let's think about the time and space complexity here. And yeah, you can probably like not sort it twice or something, and that would make it run a little faster in LeetCode, but time complexity wise, it would be exactly the same. Okay, so let's think about it here. So what are we doing? We made this robots thing, which is going to be big O of n. So we already have something big O of n because we went through positions. We sorted it, so that's going to be n log n, which is, and by n I mean the length of any one of these, that they should all be the same length, positions, health, directions, and so on. Okay, now we made our stack, but our stack isn't going to cost us anything more because the most a stack can ever be is the length of the robots. So that's not going to cost us anything. We go through the robots one time. That's big O of n. That doesn't cost us anything. Okay, we do these comparisons, but this doesn't cost us anything either. And then finally, we sort the stack, which is going to be n log n worst case. And realistically, if there's a bunch of collisions, the stack should be shorter than the robots. So that's not going to cost us anything either. So it's just n log n solution. And then for the space, so for this robot, we did actually store like all of these things, which would be like 4 times n or something, right? Because we have these 4 things, but because this is a constant, we can just get rid of that. The stack will be at most n length, so that's not going to cost us anything. The result we usually don't count because it's the result. So this is just a O of n solution for space and n log n for time. And yeah, that's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.